Hi class, we're on to the next video. This next section is for chapter 7.4, geometrically defined vectors and their applications. We will go over some basic terminology, the equilibrium, incline applications, and navigation applications. So mostly we're going to talk about adding vectors together and what that looks like geometrically. Okay, so here's some basic terminology to start off with. First is scalar. Okay, we generally call a single real value a scalar. So a scalar is generally a whole number, a fraction, a rational number, an irrational number, just any single number, basically. Okay, it represents the magnitude of a quantity, and it can be represented by, again, a real number, right? A vector in the plane is a directed line segment. So what that means is it's basically an arrow, okay? And the length of the arrow that we have represents certain things. So the length of the arrow is important. We'll get to that in just a second. Right? So this would be a vector. It has a tail and it has a tip, okay? We call this the initial side. We call this the terminal side, okay? So when we give a vector a name, we generally write that vector name in boldface. If it has an initial point and a terminal point, we write it in terms of the initial and terminal points. Okay, and it tells us, again, we start with the initial point, we end with the terminal point. Have a labeled initial and terminal side. A lot of times the vector will be just called X or V or Y. So we'd use boldface, whatever the name is. Okay. Another representation that we have is to use the same name but with a arrow over it. Okay. Okay. This is an alternate form of writing the same sort of vector. Okay. So again, O here is the initial point and P is our terminal point. The magnitude of a vector is represented by how long the vector is. Okay. So the length of a vector represents its magnitude. Okay. The way that we write it is we put the name of the vector inside of the absolute value signs. Now this does not mean absolute value. There's actually a function that you use to calculate the length of a vector. It is not absolute value. It's just a notation. Okay. We say two vectors are equal if and only if they have the same magnitude and same direction. Okay, so they have to point in the same direction and they have to be the same length. They have different lengths, but the same direction, they're not equal. Okay. So the vectors OP and here PO, because again, this is my initial side and this is my terminal side. These have the same length, but they're pointing in opposite directions. So these are not the same. Okay. However, their lengths are, right? So the magnitudes are, but the vectors are not the same because they have opposite directions. Right. Here, these two vectors point in the same direction and they are equal in length, so they are the same vector. Okay. Same thing here. Same direction, same length. Okay. Here, A and E may have the same length, but they're not pointing in the same direction. Here, A and F are pointing in the same direction, but they do not have the same length, so they are not equal either. Okay. So adding two vectors together. The sum of two vectors is also another vector. Okay. We call it the resultant. So if I take a vector A and a vector B and I add them together, I have a resulting vector that I call the resultant, right? So here, let's start with the vector A and let's have a vector B. So here what we're doing is we are putting the two vectors tip to tail. Okay. So it doesn't matter where in space A or B are, they're always the same vector because of their length and the direction they're pointing. So if this vector B was moved over here or anywhere else, it's still the same vector B because of its length and the direction it points. So when I move vectors around, I can pretty much put them wherever I want to, right? So one way of adding two vectors together is to place them tip to tail, right? And it really doesn't matter which order it goes. For instance, I could have had B first and then put A off of B, right? But here we're adding A and B, so we write A first and then the next one, tip to tail, is B. Okay, but it doesn't really matter. You'll always get the same vector. So geometrically, the way that this works is that when I place these tip to tail, I draw a brand new vector that starts at the starting point of A and ends at the end point of B. So my new vector's initial point will be the same initial point of vector A, and its terminal point will be the same terminal point as B, right? So I'm adding these two things together to create a new vector that is A plus B. So that's one way to do this, okay? That's again called the tip to tail method. Another way to do it is called the parallelogram method, right? And so what you do is, again, like I said, it doesn't matter where I place B because B is always the same vector because it has a length and a direction. So instead of placing it tip to tail with A, I put the two initial points together, okay? So they have the same initial point. So now this creates the base of a parallelogram, okay? It's half of a parallelogram. So I draw the rest of the parallelogram, and the diagonal of that parallelogram is that same vector A plus B. So right now, if I were to take A plus B and move this one onto that one, it would be the same vector. Okay, so let's kind of shy away from this presentation a little bit and go to Desmos and play around a little bit, and I'll show that to you with some animations. Let's talk a little bit first about graphing a vector. Let's say that we actually have the components of our vector, meaning we know what numbers make it up, okay? We'll touch on this a lot more in the next video. I'm just going to discuss it now so that we can have a better understanding of the visuals that we're going to see. So if I have a vector that is, let's say I wanted to reach the point 8, 6, okay? What I would do is I would draw a line, okay, until I get to 8, and then I'll draw a line up until I get to the point that I want, okay, at 6, right? And then once I find that position here, I'll draw my vector. So my vector, the initial point will start at 0 and it will end at the place that I want it to go, okay? So I'm really just showing you guys how to graph these things. As you can see already, it's formed by a triangle, which is why it's covered in a trig class, because all the things that we're going to talk about for vectors is really just sines and cosines, right? The stuff that you guys already know about, okay? Now, what I was saying was, this same vector doesn't matter where it is in space, okay? We just choose to represent it as starting at 0 and then going to wherever I want. But if I were to move this up and down in some form, okay, it's always the same vector, okay? So it doesn't matter where I put it in space, it's the same vector, right? I can start to move it all over the place. It's always the same vector. All right, so now we'll talk about what it looks like to add vectors together geometrically. So let's say I have a vector that I call u, okay? So this vector is represented by the points 5, 5, right? I go over 5 and up 5. And let's say I have another vector that I'll call v, okay? V is represented by 4, 1, okay? So these are my two vectors. Here we're saying that these are the initial points. I just didn't draw the arrow tips, right? But we can use these points as the tips of the arrow, okay? It's hard to draw the arrow tips actually on this. So if I want to add these two vectors together, okay, then one thing that I would do, right, so I'll just kind of let this animation play and you can figure out which way we're doing, if we're doing tip to tail or parallelogram. So the position of the vectors now should kind of give you a tip to what kind of method we're going to do, right? So to draw a parallelogram, I basically redraw this vector here tip to tail, right? That's going to make the other side of my parallelogram. I do the same thing for my other vector, Okay. So that makes my parallelogram here. And then my addition of these two vectors is the new diagonal across. Okay. And notice, if I look at the x position of one vector and the x position of the other, me adding those two vectors results in the sum having an x position of the sum of those two x values. Same with the y. 5 and 1 gives me a 6. Okay. And again, that's not super important for right now. We will talk about that in the next video in depth. I'm just pointing some things out to you guys. Okay. So again, what I did was I drew out my parallelogram. Okay. And then you draw your diagonal, and that's your new vector. Okay. That would be the sum of the two vectors there. All right. So I can take these off so you can see that. All right. So let's look at the tip to tail method. Take the same two vectors. So we call this the standard position. Right? So standard position, again, is that the initial points are starting at the origin. Okay, so we're having these vectors in their initial positions, and I'm going to move one of these to be tip to tail with the other. In this case, I'm going to move my v vector to be tip to tail with my u. And now when I add those two things together, I will have the exact same vector. It still ends at 9, 6. Okay, so I'm adding the pieces together, and I'm still getting that same terminal position. Okay, let's set they're the same. So that's how we add vectors. That's what it looks like geometrically, or how to do it on a graph even. Okay, so coming back to our presentation, you can see that it's the same thing, and that these two vectors, resultant vectors, they are identical. They are the same. Okay, the sum of vector v and its opposite, negative v, has a magnitude of 0, and it's called the 0 vector. Okay, very important vector. If we want to subtract vectors, what we do is we add our vector to the opposite of one of the vectors, right? So if I want a minus b, I'm going to add a to negative b. Okay, so here you go. I have a and b. So again, they're in the standard position, right, where they are their initial points are at the same point. Okay, I take b and I make negative b, so it goes in the opposite direction. Okay, and then now I would create the parallelogram here to form out my resultant. Okay, so I still have my parallelogram, but it's made with this as one side and this as one side because I'm adding a plus negative b. Okay, the scalar product of a real number k and a vector u is k times u. So remember what we said right at the beginning, a scalar is just a real value. It's called the scalar product because what it does is it scales your vector. It makes it longer or shorter by a value of k, by a factor of k, I should say. So if I have 2 times u, it's whatever my vector u is, but it will make it twice as long. Okay, so it changes the length of your vector. Okay, the magnitude of it, the length, will be absolute value of k times the magnitude of that u that you already had. Okay, so for instance, if this is u, this would be double u, right? 2 times u. This would be 3/2, 1.5 u's. This would be half of a u, and this would be negative 2 u's. So again, let's look at what this looks like, and let's go to our Desmond's presentation to animate this for us. So let's take a vector u. Okay, here u ends at the point 2, 2, right? So if I multiply that u by a scalar, this purple vector here, it's 1 u's. It's the same value as u. It's the same length. Everything is the same. Okay. Now if I change it to 2, it's twice as long, right? If this is a u, this is 2 of them. It's one on top of the other. Notice what it does to the values that compose the points of u. All right. If u ends at 2, 2, twice that will end at 4, 4. Okay. Again, we'll see that in the next video. You're just getting a preview of an overview of vectors at this point. Okay. Now, if we play this as an animation, right? So this is really just keeping track of how much of a u we have, right? So if I make this to be 0.5, for instance, it's halfway there. Okay, so my scalar scales my original vector. If I want half of u, it'll scale it down to half the size. If I want 4 times u, it'll scale it to be 4 times bigger. Everything about it will just change by that scalar factor that I have, right? But the direction stays the same. So it just changes the length. It makes it shorter or longer. Okay, that's what a scalar does. Okay, now let's take that same vector u that we had, and this time we're going to do a negative scaling. So if I have a negative scalar value, it changes the direction that my vector points, and it scales it into that negative direction, right? So if I have a negative 1u, for instance, it is the same size, okay? It's the same size as my original, just in the opposite direction, just like we saw with that negative b, okay? And it'll just grow it in the negative direction as much as I need to, okay? So that's what a negative scalar does. It just changes the direction, and then it makes it longer or shorter as well. Talk about subtracting vectors a little bit more. So we're going to talk about 2 methods of subtracting vectors, actually. One of these are not in your book, so there's a new method that you'll learn that may help you to understand what these things look like. So again, let's take a vector u. Okay, we'll call it 5, 5. Our vector v will be that 4, 1 that we had. Now, if I want to subtract these 2 vectors, u minus v, I would take my v, just like we saw in the presentation, where it was a plus b or a plus negative b. I need to make v go negative, right? So it needs to be the opposite value. So if you notice what happens when it goes in the opposite value is that the values inside change. You're basically multiplying everything by -1, right? So it goes in the opposite direction. You notice it still stays on a straight line, okay? And now what we'll do is we'll just do our parallelogram, okay? So I will move this over, right? This is now one side of my parallelogram. So if I just take this same length and I draw it over here, same thing here, take this negative v, move it up to the top portion, okay? And that creates a parallelogram for me, right? And if I draw from where these 2 vectors meet, and I draw that diagonal, okay, then that is going to be my resultant, right? So that's my new vector. And notice that it's the sum, right? 5 minus 4 is 1, and 5 minus 1 is 4, right? So we'll talk about that again in the next video, but you subtract the components. Now, the other way that I was talking about, okay, was to all right, let's get rid of this parallelogram, okay? So another way to do this is to draw it in standard position, okay? And so remember that this is the tip and this is the tail, so they're 2 tails together. So you draw it in the standard position, and then you connect the 2 tips together, and that's the same as subtracting your vectors, okay? So notice if I were to bring this over, it lines up perfectly, right? So then this is the triangle method, right? So just like when we're adding, we had tip to tail. This kind of does the same thing, but my little tip to tail here is actually the subtraction resultant that I was looking for, okay? So again, if this is u, our scalar just scales and changes the direction, and it only changes the direction if it scales it in the opposite direction with the negative scalar. Okay, so now let's talk about properties of parallelograms, since we're adding and subtracting vectors using parallelograms. Parallelogram is a quadrilateral, 4-sided figure, right, whose opposite sides are parallel. The opposite sides and opposite angles of a parallelogram are all equal, and adjacent angles of a parallelogram are supplementary. Okay, so let's come back to a picture of us and flesh this out a little bit. Okay, so this angle and this angle are equal. This angle and this angle is equal. Okay, the angles are supplementary. Any adjacent angles are supplementary, so any two angles that kind of share a side are going to add up to 180. So this angle and this angle will add up to 180. This angle and this angle will be 180, right, because they share a side. These two angles share a side as well, so this one and this one add up to 180. Same thing here. This angle and this angle will add up to 180. Okay. And so for the last one, the diagonals of a parallelogram bisect each other, okay, meaning they cut each other in half, but do not necessarily bisect the angles of the parallelogram. So again, what does that mean? So if we take this parallelogram, so this diagonal, if I were to draw another diagonal here, it would cut this diagonal in half, okay? This other diagonal would also be cut equally in half, right? However, this, so you have the parallelogram, right? You cut it in half with a diagonal, and you can see you have two triangles here, a triangle here, right, and a triangle here. The angles here are not the same. It does not bisect the angles. So this half angle here and this half of an angle are not the same. This half of an angle here from this side to this side is not the same as the angle formed by this side and that side. Okay, so it does not cut the angles in half, but the two diagonals will cut each other in half. Okay. Okay. So let's do an example, right? So two forces of 15 and 22 newtons act on a point in the plane. So again, the forces here, this represents the magnitude of a vector. Okay, magnitude is length. It can also represent force. So it's this vector, right, that represents the 15 newtons is going to be a shorter vector than the vector that represents the 22 newtons, right? So again, the lengths here are different. Okay, so a newton is a unit of force. Okay, so equals 0.225 pounds, just for future reference if you haven't taken any physics courses. If the angle between the forces is 100 degrees, find the magnitude of the resultant vector. So these two vectors have an angle of 100 degrees between them, and I want to add these two vectors together, and I want to know what the magnitude of the vector that we get out when we add these two together is. Okay. So let's look at the picture. Okay, so I got P and Q and S. So I have an initial and a terminal, an initial and a terminal. 15 and 22. So again, the force of 15 is shorter than the force of 22, right? So it represents the length of the vector. So force vectors, a longer vector on a force vector means more force. Okay, so the angle between them is 100 degrees. Okay, and then we can draw out our parallelogram, right? So it's a parallelogram, so that means that the side opposite are the same length. So 15, 15, 22, and 22. And this is our resultant vector that we want. We want to find the value of V here. Okay, so what we want to do is the angles of the parallelogram adjacent to angle P are going to measure 80 degrees, right? Because if this is 100 and this is 100, these two have to add up to 180. So I know what the angles here on this side are, right? Because they're supplementary. So now that I know that these are 80, right, I have a lot of information, but there's one thing that I don't know, right? So I want to use some information that I know about triangles, right? Because as I said before, whenever you have vectors, you have triangles, right? There's no 90 degrees here, okay? But we do have a few things to help us still figure out information regarding triangles, right? So we have the law of sines and law of cosines. So we just got to figure out which one is appropriate, okay? I have a side, an angle, and a side, right? So I should be able to use some sort of ratio to find that missing side that's across one of these given angles, okay? So I can use the law of cosines here with either of these triangles. So if you remember your law of cosines, you put in the lengths of the side and you square it. This could be A, this would be a B, and then you find the cosine of the angle you do have, right? So b squared, okay, is going to be 15 squared plus 22 squared minus 2 times 15 times 22 times cosine of 80 degrees. Okay, so we're using our law of cosines here, and all of this stuff we can plug in to get a approximate value. Okay, that's the squared length. So I got to take the square root of this, and it's about 24. Okay, so just make sure to watch out for rounding errors when you do this. So the magnitude of the resultant vector is about 24 newtons. Okay, so when I add these two together, I get a resulting force in this direction that has a length or force value of 24 newtons. Okay, so the equilibrant. Sometimes it's necessary to find a vector that will counterbalance a resultant. Okay, counterbalance resultant. So this opposite vector is called the equilibrant. The equilibrant of vector u is a vector negative u. Okay, so here's our example. So we want to find the magnitude of the equilibrant of forces of 48 newtons and 60 newtons acting on a point A. Okay, if the angle between the forces is 50 degrees, then find the angle between the equilibrant and the 48 newton force. So basically what we're going to do is the exact same thing that we did in the last example. We're going to find that resultant vector. Okay, we're going to find the magnitude of our resultant vector, but we're going to find it in the opposite direction. Okay, so we're going to find it in this direction. And then what we want to do is we want to find the angle between it and one of the given vectors. Okay, so we're basically doing the same thing. Then we're going to take this vector v, we're going to wrap it in the opposite direction, and then we're going to find the angle that's formed between it and one of the given sides. Okay. All right. Okay. So I have my vector. All right. I have the 48 newton. I have the 60 newton. The angle between them is 50 degrees. Okay. So I can draw my parallelogram, right? And then the resultant vector is, as you can see here, it'll be in the middle. Okay. So once I find this v, I'm going to take it and I'm going to draw it in the opposite direction. Okay. So same length, just change the direction. Okay. Then I want to find the angle between it and the 48 newton vector. Okay. So this alpha is the angle I'm trying to find. So first I got to find this vector, right? And then I want to find the angle between it. All right. So let's go ahead and do that. So the equilibrant is negative v. Okay. So we'll keep this here so that we can reference it as we work. So the magnitude of negative v is the same as the magnitude of v. All right. It's the same length. So we again use our law of cosines. All right. So 48 squared, 60 squared, we plug that all in, and the angle that I'm using again is this angle here because I'm trying to find the angle across it, right? Or I'm sorry, the side across from this angle. So I'm using this triangle, okay? And then it's the 48, the 60, and the 130 that's given, and this is the v squared that I'm calculating. I can plug in all my values, take the square root, and I get about 98 newtons. So I know that this is 98. Okay, it has a magnitude of 98, I should say. Now what I want to do is I want to find the angle alpha between it. Okay, so that angle alpha can be found by subtracting the angle CAB, right? CAB from 180 degrees, right? Because this V is a straight line, right? So this whole thing is 180. Alright, so if I find just this piece, it's not 50. 50 is this whole part right here. Okay, I need to find just this part, And you can't say, oh, well, this should just cut in half, right? Just because that's what it looks like in the picture doesn't mean that that's what it's doing, right? So I have to actually find this length here, and then just subtract this length from 180 so that I can figure out what this alpha value is going to be, right? So I'm going to use the law of sines to find this angle here, right? So again, I have a triangle, right? This CAB triangle, and so I can use my, in this case, law of sines. So I know that whatever this angle is over 60, or 60 over sine of this angle, would be equivalent to sine of 30 over b, or however it is I want to set that up, right? So sine of CAB over 60 will be the same as the sine of 130 over the length 98 here. And I can start to solve this. Right, you can do cross multiplication. So sine of CAB will be 60 times sine 130 divided by 98, which will give you this value. And I want to find the actual value here, so I'll use my inverse sine in order to figure out what the angle CAB is supposed to be. So it'll be about 28 degrees. Okay. And so alpha is 180 minus 28, which gives me 152 degrees. Okay. So let's move on to the next example. Find the force required to keep a 50-pound wagon from sliding down a ramp that's inclined at 20 degrees to the horizontal. Okay, so from the ground, it's forming a 20-degree angle. Okay. We're going to assume that there is no friction, so we don't have to take that into consideration, which we couldn't do at this level in our class anyways. But we should have an illustration of something similar to this, right? So again, here is my ramp. It has an angle of 20 degrees. The wagon is 50 pounds. So that means the force of the wagon due to gravity is 50, right? So it has a downward weight towards the center of the earth, straight down, right, of 50 pounds. Okay. This incline here is because it's on a ramp, right? So there's also a force pulling in this way, and then we have a small force vector here that's keeping it from sliding down the ramp. Okay, so we're looking for this vector right here, AC. It's equal to this vector F. So we have our vector straight down. We have this force that's being pushed onto the ramp. So you can see it's perpendicular to the ramp. It forms a 90-degree angle, and so this angle here is going to be the same as this angle of 20 degrees, right? So it's basically, this is basically the ramp all over again, but with vectors instead of sides, right? So the vertical force, BA, represent the force of gravity. It's 50 pounds because gravity is pulling downwards, right? BA is equal to BC minus AC. Okay, so if you look here, I have that tip to tail thing going on again with my triangle here, right? So if this was considered the origin and I had one vector coming out and another vector coming out, I'm connecting their two tips together, right? And that was the same way that I had, 5 minutes ago or so in my demonstration of the method of subtracting vectors that was not mentioned in our book so far, right? The other geometrical representation of that, right? Which is to connect the two tips together when those two vectors that you are subtracting are sharing their initial point. Okay. So here, the vector BC, okay, this one right here, represent the force with which the weight pushes against the ramp, right? So there's a force coming down due to gravity, and since there's a force down, it's also coming into the ramp, which is what is keeping it from sliding down, basically. Okay. So this is what we're going to use to solve, right? So our vector BF, this little one here, represents the force that would pull the weight up the ramp, right? So it's the force acting up the ramp to keep it from pulling down. And the vectors BF and AC are equal. So the magnitude of AC gives the magnitude of this F that's required, right? So BF and AC are parallel. They're the same vector, right? Same length, same direction. Okay, it's just that one is down here and the other one is up here. So remember what I said? It doesn't matter where in space it is, right? And that's what we're doing. So we're drawing a diagram to help us to figure out what this needs to be, and it's basically just being moved somewhere else into a right triangle, which we know how to solve. Okay. So since angle BDE, okay, BDE and angle C are right angles, so I have two different triangles here. Okay. Triangle CBA, so CBA and DEB, right? So that's my have two corresponding angles that are equal, right? Which is the 20 and the 20 and the right angle. And so that means that they are similar triangles, right? Basically, they have all of their angles are the same, right? Therefore, the measure of angle ABC equals the measure of angle E. Okay, so this E and this ABC angle, this 20 and 20, they are the same, as we already know. Okay, which is 20 degrees. Okay, so from right triangle ABC, sine of 20 is going to be AC over 50, right? So this is the hypotenuse here, so it's 50, so it's the opposite over the hypotenuse. So AC is 50 sine 20 when we move this stuff around a little bit, right? And then we can figure out what that value is. So a force of approximately 17 pounds, okay, will keep the wagon from sliding down the ramp. All right. So same sort of setup, obviously a little different, right? So a force of 16 pounds is required to hold a 40-pound lawnmower on an incline, right? So that's this vector. This BE is going to be the 16 pounds, right? So as you can see, we equated those. So what angle does the incline make with the horizontal? So here we're trying to find this theta, right? And so we already know from our last example that this theta is equal to CBA, right? That's the equality that we have here. So we're really just trying to find, we're going to use this triangle again, try to find CBA. So here we have a side 16, we have a 40. So we have, again, information for sine, right? I have the opposite, I have the hypotenuse. I can figure out what sine is. If I know what sine is, I can figure out inverse sine in order to find this angle. So that's sort of the direction that we're going to go, right? So vector BE represents the force required to hold the mower on the incline, okay? That's why we can equate those. In the right triangle ABC, the measure of angle B here is equal to theta. The magnitude of vector BA represents the weight of the lawnmower, okay? And the vector AC equals BE, right? So AC and BE are equal. Okay. Sine of B is 16 over the 40, which is 0.4. So then that means that B is 23.6 degrees. So you would just use sine inverse of 0.4 and you'll get out 23.6. Okay. So the hill makes an angle of about 23.6 degrees with B horizontal. Okay, so for the next example, a ship leaves port on a bearing of 28 degrees and travels 8.2 miles. The ship then turns due east and travels 4.3 miles. How far is the ship from port? Okay, what is its bearing from port? So remember, we always want to draw a picture. So if this is north, okay, we turn 28 degrees and we go for 8.2 miles, and then we go due east for 4.3 miles. Okay, so we want to know what its bearing is from port. So we need to find this angle, and then we can add that to 28 degrees so that we have its entire thing. If we want to know how far it is from port, we would do the same thing, but we need to find the magnitude of this vector. Okay, so that's what we're doing. All right, so we have a triangle. Again, it is not a right triangle, so we need to use either law of sines or law of cosines, I would presume. And it looks like we have a side angle side, and the one that we want is across from the angle that we know. So it looks like we would be using law of, that's right, cosines. Okay, so let's get through this presentation and see what it says for us. Okay, so the vectors PA and AE represent the ship's path. Okay, we're seeking the magnitude and bearing of PE. Triangle PNA, PNA, right? The smaller triangle here is a right triangle. So the measure of angle NAP, NAP is 90 minus 28, right? So I know this angle, and I can figure out this angle. And that's how I'm finding this 118. Okay, 62. And so since I know that this is 62, I know that this has to be 118 because that's a right angle. Okay. So the measure of PAE, we actually just talked about, is 180 minus 62. It's going to be 118. Okay. So we're going to use the law of cosines to find magnitude of PE, right? I need a magnitude of this vector. So again, law of sines. So I have PE is 8.2 squared, 4.3 squared minus 8.2 times 4.3 cosine of this angle. Okay, and that gives me 118. Again, that's the squared value, so I need to take the square root, and that is 10.9. Okay, so the ship is about 10.9 miles from port. So that's one of the values we have. We also need to now find this angle so we can get the bearing. Okay. So to find the bearing of the ship from port, first find the measure of angle APE, right? So we need APE here. So we're going to use the law of sines. Okay, again, I have a lot of information given. So since I'm trying to find an angle here, we'll use the law of sines. So we can say that 118 and the magnitude of this that we just found, which was 10.9, is equal to 4.3 over the sine of this angle, right? Oops. So APE, this angle over 4.3 is equal to sine of 118 over the magnitude of this, which is 10.9. So we can move things around to figure out what sine of this angle is. Once we have sine of this angle, we use sine inverse in order to figure out that our value is 20.4 degrees. Okay, so now we add those two values together and we get 48.4 degrees. That is our bearing. Okay, so now we're going to talk about airspeed and ground speed. I think we have one more example. We have one more example. It's a long one, however. So let's talk about airspeed. Okay, so airspeed and ground speed are different. Your speed in the air is different than it is relative to the ground, right? So the airspeed of a plane is its speed relative to the air. The ground speed of a plane is its speed relative to the ground. The ground speed of a plane is represented by the vector sum of the airspeed and wind speed vectors. So here we go. If this is north, so course and ground speed, the actual direction of the plane. Okay, so it's going to be the sum of its bearing and airspeed, and then the wind direction. Okay, so obviously the wind is pushing it a little bit, so it's adding to its speed, and it's also going to cause it to drift off course a little bit, right? Because you're pushing against the wind, so it has an effect on where you're flying, right? So when we want to have the course and ground speed, we're going to add together its airspeed and its wind direction and speed. All right. So here's our example. Okay, an airplane that is following a bearing of 239 degrees at an airspeed of 425 miles per hour encounters a wind blowing at 36 miles per hour from a direction of 115 degrees. So we want to find the resulting bearing and ground speed for the plane when we take into consideration the wind, right? So here's our graph. So I'm at a bearing of 239 degrees. I am 425 miles per hour. So my speed is my magnitude, right? So I have an angle here at 59 degrees from the north-south line. Here is the wind speed. Okay, so this is an angle of 36 degrees, and it is at a bearing of 115 degrees, right? So the difference from the east-west line is 25 degrees. Okay, so this is the angle that's formed between these two, right? So I'm flying this way, I'm getting pushed in this direction, so I'm going to add that vector to it, and then I need to find the results, right? The result of these two vectors being added together, right? So I'm looking for the B. I'm looking for B. Okay. So vector C represents the airspeed and bearing of the plane. Okay. C is the airspeed and the bearing of the plane. Right. Vector A represents the speed and direction of the wind. Okay. Again, A is the direction of the wind. Right. Angle ABC has its measure the sum of angle AB N1 and angle N1 BC. So we're looking at A, B, C. That's the angle we're looking at. A, B, C. The angle that's formed between the two. Right. And so what it was saying, we'll go back to it, is that A, B, N1, okay, and N1, B, C being added together is the entire angle. So they're just saying that you can split it up into two parts. Okay, so here and here. So okay, so angle SAB is 239 minus 180. So we'll keep going back and forth. Apologies here. All right. So SAB, right? SAB, that's easy to figure out because you have 239, and so you just minus off this 180 degrees to get what's left over, which is that 59. Okay, and they'll do the same thing here for this 25. It'll be this 115 minus off the 90 to leave off the 25. Okay, so let's go through that a little bit. So south AB is 239 minus 180, which is 59. And because angle ABN is an alternate interior angle to it, ABN is 59. Okay, so here you have two parallel lines, okay, and an intersecting line. So then we can equate some of these angles from the two parallel lines and the intersecting line between them. So this angle here, this 59, is equal to this angle here, this N1BA, right? And that's because, again, you have two parallel lines, you have the intersecting line, so you have, what is that? Alternate interior angles, right? So from here to here is an interior angle. This would be exterior angles, right? This is that alternate interior angle. So this is 59, and this is 59 as well. Okay. So for the next one that we have, so angle E1BF is 115 minus 90, which is that 25 that we got. Okay. This same reason, this angle CBW1 also measures 25 because it is a vertical angle. Okay. So let's go ahead and look at that as well. Okay. So we know that that here E1, B, and F is 25. So the angle across from it is also going to be 25. So W1, B, and C, right? They're across from each other on a four-way split, right? So they're vertical angles, so they are the same. So this is 25 and this is 25. So I know that this is 59. I know this is 25, and I know that this angle that's missing, this C, B, and 1, plus the 25 here needs to be 90, so I just go 90 minus 25 to find that missing angle here. Then I add them together. Okay. Okay. So again, N1B C is a complement of 25 degrees, so that gives us 65 degrees. Okay. So we add those together now, 59 plus the 65, that gives us 124. So if I want to find the magnitude of B, we're just going to use the law of cosines, right? So let's look at again what we have so far. Okay. So now I have this angle. I got this side. I got this side. We'll use the law of cosines in order to find the magnitude of B. All right. So using our formulas, magnitude of B squared is the magnitude of A squared plus magnitude of C squared, and so forth. We plug in our values, right? My two sides, and then the angle that I have, and I will get B squared is almost 200,000, and so again we got to take the square root, which is about 446. So that is the magnitude of B, right? So now we want to find the bearing. Okay? So I want to find the bearing. So I need this angle A, or alpha. I'm sorry. So I can find alpha. I just add it to 239, and then I have the bearing of alpha. So again, I use law of cosines to find the magnitude. Now I have a lot of information, so I can start to use the law of the law of sines. So I know sine of alpha over 36 is the same as the sine of, what was this, 124 over the value we just found for B, which was 449, I believe. So that'll be our equation that we use in order to find alpha. Okay. So again, we must find the alpha and then add it to 239. So we're going to use the law of sines, and then that's our setup. Okay. So sine of 124 over 446, sine of alpha over 36. We solve for sine of alpha, multiply both sides by 36. Okay. Take the sine inverse of this value. Right, and that'll be my alpha, which comes to about 4 degrees. Okay, so adding those together, and our resulting bearing is 243 degrees. All right, thank you guys. I'll see you on the next video.